All right, so you're in for a treat today, because today we're going to do the best part of the course, Cochran's theorem. It's the only theorem we're going to do in this course, and it's really the most important thing because it justifies everything we're going to be doing. Analysis of variance is all about decomposing different parts of variance for our data. And Cochran's theorem is going to tell us how we can test that statistically. So let's go check that out. All right, so welcome back to the third lecture we have here in the remote version of Design and Analysis of Experiments Stat 568 from the University of Alberta, or from my basement direct to your house. Now, today what we're going to do is we're going to do the perhaps one of my favorite lectures, the mathematical portion of the course, because all of this theory that we're doing is rooted in, well, mathematics and probability theory to make it valid. So we're going to focus on that today, and then moving forward from this lecture, we'll be discussing lots of other design settings. So if we can just get through this one, then we'll get into all these different ways that you can set up different multi-factor experiments. But we got to do the actual math first. So going forward, all right, good, I'm still recording. I'm a little paranoid that I lost the audio again. Right. So the first question is, why are we doing F-tests, right? I mean, I keep talking about these F-tests. Why in the world are we actually doing them? So starting now, we have question of why do F-tests? Okay, so that's a good question. Well, the reason is we talked a little bit about this before, that we have that the air sum of squares has a chi-squared distribution with, well, in our one-way ANOVA setting, n minus k degrees of freedom, the one-way ANOVA from the previous lectures. When we get to multi-factor and other types of experimental designs, then the residuals will be a little bit different. But right now, we still have these degrees of freedom. Right, and we also said that the treatment sum of squares in our one-way ANOVA will have a chi-squared distribution with k minus 1 degrees of freedom under the null hypothesis. Okay, so distributionally, that means that if we take the ratio of the two of these things and divide by their respective degrees of freedom, then we get an F distribution. But that doesn't tell us, that tells us that we have an F distribution under the null hypothesis. It doesn't tell us why we should actually use this and why this is the a valid or the best thing we can do under all the strict assumptions like normality and IID errors, etc. So the reason why we actually want to do this and use the F distribution comes from something called the likelihood ratio. So if you've taken, I don't know, a second year undergrad course in stats, or perhaps a math stats course, I'm not exactly sure when they teach likelihood ratio, but it is really a fundamental tool. So in case you haven't seen it or you need a little refresher, right, the likelihood ratio in our parametric statistics here is going to be the, well, the likelihood of, okay, I guess I can write out, we'll use theta, I guess, as our generic parameter vector, general parameters. So, and maybe X, I guess, or maybe Y, since our response variables are always denoted Y in this course. Given, so this is the likelihood of the, right, there's the function of the parameters given the data Y under the null hypothesis. And then we have the ratio on the bottom of the ratio, which is going to be our likelihood under the alternative. And if we go back into some classical statistical theory, we get results like the Neyman-Pearson lemma, which says, okay, hand waving, because I'm not going to write it out precisely, but in a hand wavy sense, it basically says the likelihood ratio test is the best thing to do. It's the most powerful test when comparing simple hypotheses. Simple hypotheses, which are point hypotheses. That would be like saying the mean is 1 or the mean is 2, and I want to compare that. That's not the case that we're in. We're asking questions like the mean of A is equal to the mean of B, or they're different. So those are not simple hypotheses, but you can still extend this idea to that setting. So I'm not going to get into all the specific details, but the idea is that, right, we have the Neyman-Pearson lemma, but I should say the little side note, which is this is also extendable in some cases beyond simple hypotheses. And if you want, we can go through and actually do some examples of that, say in office hours or discussion portions, live discussions of the lecture. But for now, I just wanted to point out that you can do this. And for our course, I'll say, and it turns out that, well, I'll just write it all out. It turns out that the likelihood ratio test, LRT, which I also used to use to get to U of A, but not anymore now that I just stay home all the time. Anyway, it turns out that the LRT is equivalent to the F-test in the ANOVA setting, right? The likelihood ratio test is not always an F-test, but in the case that we're actually want to test the hypotheses of one-way ANOVA that we're discussing, then the likelihood ratio test is equivalent to the F-test. And you can show this. You have to write out the likelihood based on the normal distribution. Again, we're assuming that the errors are IID and have a normal distribution for this to be valid. So it's a very strong assumption, but it's still valid enough in practice most of the time. Regardless, the idea is that if you were to write down the likelihood under the null for the normal, divide it by the likelihood for the alternative under the normal distribution, and basically just cancel terms, push everything around, you can derive the likelihood ratio, you can derive the F statistic, which is actually quite a neat thing to try. So I encourage you to try it on your own if you're interested in the mathematical derivation. Perhaps we can do this in a live discussion offline or online, off video, I guess, off pre-recorded. Anyway, that's really the main thing I wanted to point out about the F-test. Is that there is more reason for doing it rather than just saying, this ratio happens to have an F distribution. Well, actually, there's more to it, which is that it's actually the right thing to do in this restrictive parametric setting. Right. But going forward, that leads to an even more fundamental question. We'll say even more fundamental question, which is why do sums of squares have chi-squared distributions? And there's another thing that I realized I did not point out in the previous lecture, a little bit of a subtlety, and the other that I should point out, which is why are the treatment sum of squares and the error sum of squares independent. Because up above, where I said that the ratio of two chi-squareds normalized by their degrees of freedom has an F distribution. This is only if the treatment and the error sum of squares are independent. Yeah, close enough. Yeah, so it only works if those two objects in the numerator and the denominator are independent of each other, and furthermore have a chi-square distribution, at least under the null hypothesis setting that we're interested in. So why is that all true? And that's true because of Cochran's theorem. Right, so answer is C. Cochran's theorem. Hooray. So we should probably actually write that down in some formality and then go about proving it. Right, so Cochran's theorem, which takes us back to 1934. And what it says is let, we'll say Z1 through Zm be IID, independent, identically distributed, normal, 0, sigma squared random variables. And we'll say denote capital Z to be the vector of Z1 through Zm, which is an m-dimensional vector. Okay. What else do we need? We need, yes, K. Okay, so furthermore, we'll say let, I should say for, not let, for K in 1 through S. So now K is no longer going to be the number of factor levels. For this one lecture in this section on Cochran's theorem, K is just going to be an index ranging from 1 to S. And for that, we're going to say let AK be an M by M, that's a terrible M, symmetric matrix. I should say let the AK be a collection of M by M symmetric matrices with ijth entry denoted. I have a lot of indices here, so we denote it A sub ij and with a K in the numerator, in the superscript, to correspond to the kth matrix. Okay, so now we have a collection of symmetric matrices. I haven't told you what they do yet. Let's bring this to about there. That should give me enough room. And then we say let QK be a quadratic form, which is just a sum of squared things, in a sense. And what we'll do is we'll denote it by Z transpose AK Z. Which and that's the matrix vector multiplication form. If we write this out as a summation, we just have ij from 1 to m of aij k and zi zj. So what this is, it's a sum of the zi times the zj over all indices I and j with some coefficient out front corresponding to this matrix AK. Great. And then lastly, this is all still the setup of the theorem. Lastly, we let the sum I from 1 to m of zi squared be the sum k from 1 to s of the q k. All right, so what does that mean? That means that if we were to, well, it basically means if we sum up all the a's, we're going to get a diagonal. We're going to get the identity matrix. If I got that right. Yes. I'll put that in the side comments here, i.e. the sum of the matrices A, K are going to just equal the identity I. Yes. All right, so we have that, and then we are almost at the conclusion of the theorem, but we have to say denote the rank of the matrix AK to be RK. Recall that the rank is the number of linearly independent columns or rows in the case. It's symmetric, so it's not even anything we have to worry too much about. But the idea is the number of linearly independent, say, columns in the matrix AK. And then we finally get to the statement of the theorem. This is all just the setup. We'll say then, if the sum of the ranks, the sum k from 1 to s of r k is equal to m, which is the dimension of the matrix. So if the ranks sum up to m, remember an m by m matrix can have at most rank m. In this case, it's going to have some rank less than m. But if they sum up to be exactly m, actually I should say not if, sorry. We'll say then what we have is this statement, if and only if and only if what? If and only if the QK are independent random variables, independent, and that QK normalized by the variance sigma squared is going to have a chi-squared distribution with degrees of freedom precisely equal to the rank of the matrix. And that is where the degrees of freedom come from that we discussed in the previous lectures. So intuitively, I can discuss what a degree of freedom is by saying, it's the number of things in the sample we have minus the number of things we're estimating. But mathematically, what it ends up being is the rank of a matrix. It's a dimension of a linear subspace. So it is good to go through all this at least once, so we have some mathematical intuition behind what we're doing. Okay, so we want to prove this, but we're not going to attack it directly. What we're going to do is start with a lemma. We'll call it lemma 1 for the sake of this. It looks like it's lemma 1.42 in my lecture notes. So what we're going to say is now let Z1 through Zm be IID normal 0, 1. So we're just going to normalize the variance to 1 for convenience. That's okay, right? Because we're going to end up dividing by sigma squared at the end anyway. So for this lemma, everything's standard normal. We don't have to worry about some variance sigma squared in there. And then what we're going to say is let A be an M by M matrix. I'll just write that out. We don't need to use that notation. Let A be M by M matrix, be an M by M matrix. We're getting there. And symmetric, i.e., right, A is equal to A transpose. So that's the definition we have here of a symmetric matrix. Then we define Q. So if you notice, the notation in this lemma is a lot like the notation in Cochran's theorem. It's just that instead of having a collection of matrices A and a collection of quadratic forms Q, we just have one. So start with one, expand to many. Anyway, our quadratic form Q is just going to be what it was above, which is Z transpose A Z, which again is just going to be the sum over I and J from 1 to M of Aij. We can just ignore that original superscript K because it's not in this lemma. We'll say then, what's the conclusion? Well, the conclusion is that Q is in fact the sum I from 1 to M of lambda I W I squared, where, so what in the world are these terms, where lambda I are the eigenvalues. I hope you remember your linear algebra. The eigenvalues of A, the matrix A, and let's get a little bit more room here, and the Wi are IID normal 0, 1, standard normal. If you like linear algebra, you can almost think of this as using the matrix and kind of rotating the basis to get a different way to write out the quadratic form. And the fact that the multivariate Gaussian has rotational symmetry to it. But again, this is kind of beyond most of what we'll actually be talking about in this course, which is how to actually design experiments. Nevertheless, I do love a good linear algebra proof. And I've been talking a lot today, so let's just sit back and enjoy it. Okay, so what do we have? Well, by the spectral theorem, wonder if my microphone's going to pick up that crying I hear upstairs. Life at home with a toddler. Anyway, by the spectral theorem, I should say for symmetric matrices, because there's lots of spectral theorems out there. So by the spectral theorem for symmetric matrices, that basically just says is that we can decompose the matrix A into a product U transpose DU, where U is the matrix of eigenvectors, and D is the diagonal matrix, hence D, of eigenvalues. So it just says that we can decompose a symmetric matrix in this way. The matrix U is orthonormal, which means if I, multiply it by its transpose, I get the identity out. And we'll say note that U is orthonormal. I was going to write orthogonal, but in this case, orthonormal. So that means that U transpose U is equal to U transpose, which is equal to the identity. Usually, if you multiply a matrix by its transpose, you may not get the same thing as the transpose times the matrix, right? Anyway, what are we doing? Well, we're actually almost done with this as a result, because, and what we do is we define the W, right? Because all I said was W is going to be an IID vector of normals. Well, the idea is that we can define the vector W by taking the vector Z and rotating it by U. So when you have an orthonormal matrix, like a matrix of eigenvectors like this, what you're basically doing is you're rotating that vector in m-dimensional space, I guess. So what happens is here is we take Z, which is just our original IID normal vector, and we rotate it to get a new IID normal vector. By rotational symmetry, this thing still has a normal distribution, a multivariate normal, I should point out, with covariance matrix being the identity, the m by m identity. And then, therefore, we basically conclude by saying that Q is equal to Z transpose A Z by the way we wrote it originally. And what do we get? Well, we get that, then we get Z transpose U transpose D U Z. Then we combine the U's and the Z's to get W's to get W transpose D W. And if we stare at that for a second, we realize, well, since D is just a diagonal matrix, this is just the sum of the lambda, that should be an M, of the lambda I Wi squareds. And we're done with what we wanted to show, so we can write the nice little proof box, QED. And furthermore, I'm going to say note that if Wi is normal 0, 1, then Wi squared is chi-squared with 1 degree of freedom. Right, that's where we get our chi-squared with 1 degree of freedom from. And furthermore, if the Wi are IID, then the sum I from 1 to m of Wi squared is going to have a chi-squared with m degrees of freedom because I added up m of them. All right. So now to get to Cochran's theorem, we're going to have to prove a second lemma. I'm going to take a quick break, and we're going to pick up with lemma number 2. All right, and we're back. Let's do lemma number 2. Right, so for lemma number 2, to get us to Cochran's theorem, is, I'll say, given the same setup as lemma 1, the W and the Q and the A and et cetera, et cetera. So given all of those things, we're going to say if lambda 1, the eigenvalues of the matrix A, if lambda 1 through lambda R is equal to 1, and lambda R plus 1, R being the rank here, just to note, through lambda M is equal to 0 for some, I'll say for some R between 0 and M, but not actually equal to 0 or M, or it's going to make this kind of degenerate, then, well, we have two things to point out. The first is that Q is going to have a chi-square distribution with R degrees of freedom, and we're going to say Q prime, which is going to be Z transpose I minus A Z, which is kind of the complementary Q, the complementary quadratic form, is going to have a chi-square distribution with M minus R degrees of freedom. And lastly, and also, Q and Q prime are independent. Excellent. So, how do we get to that? Well, the first bit comes directly from that note that I wrote up above. So, for the proof, step one is pretty easy. Basically, the idea is that if Q is equal to the sum I from 1 to m of lambda I wi squared, then Q in this specific case, because the lambda i's, the first of them, are just 1, the remainder are just 0. So as a result, we just get w1 squared plus wr squared, and noting that the sum of independent chi-squared random variables is chi-squared, and the degrees of freedom sum, and the degrees of freedom are just 1 for everything here, we get that this whole thing has a chi-squared distribution with r degrees of freedom. Okay, so that's the very first thing we had to prove. Pretty straightforward. The second one only takes a little bit more effort. The second is basically says, is to first note that the matrix I minus A also has the same eigenvectors, which is the matrix U. So we can write this as U transpose I minus D U. And this is because U transpose times U is the identity, and U transpose DU is A. So it really just means that the matrix A and its complement, I minus A, have the same eigenvectors, which is actually kind of nice. I mean, it's mathematically not too interesting, but it's actually kind of neat, I think, when you just kind of like to look at it. Regardless, now, I minus A has eigenvalues that are going to be 0 and then 1s, where the 0s are for the first R, and the 1s are going to be for the subsequent M minus R. So if you see where we're going here, we basically just flipped the 1s and the 0s from the first part. I'll say hence, what was I writing this as? Q prime is just going to equal WR plus 1 squared through WM squared, which is going to be chi-squared with M minus R degrees of freedom. Okay, great. And then lastly, Q is a function of W1 through WR. It's just the sum of the squares of these things, but it's a function of the first R W's, and Q prime is a function of WR plus 1 through WM. And since the WI's are independent, so are Q and Q prime. Right, and then we're done. QED, we can draw the little box and feel happy about that. Okay, so hopefully that makes sense. Basically, the idea is that if I have some random variables that are independent, Q depends on some of them, Q prime depends on the other ones, and they don't mix. They don't each depend. They don't have a common W that they both depend on. Since they depend on disjoint sets of W's, the independence kind of carries through in some hand-wavy sense. But this is good because now that we have our two lemmas, we can actually sit down and prove Cochran's theorem. So let's do this. Proof of Cochran's theorem. All right, so how do we do this? Well, we're effectively going to do these lemmas iteratively for each of the AK, K running from 1 to S, if I recall. I think it was S, if I recall the notation. So first, we'll use one of our mathematical jargony things and say, without loss of generality, W log, without loss of generality, let sigma squared be 1. Otherwise, we can just divide everything by sigma squared or sigma to normalize it. Hence, we normalize or standardize or whatever you want to call it. It just makes it a little bit easier to work with. So, all right, remember that if we go back up here to what Cochran's theorem said, it actually is an if and only if, which means we have to prove both directions. So then we figure out, where do we want to start? Well, we're going to start on the right-hand side, assuming independent, and then prove that the ranks have to sum up to what we want. This is the, I guess, easier way to approach it. I guess the simpler direction of the proof. It's usually nice to start with the simpler one first. So step 1, which is going to be this implication, is assume the Qi are independent, and that the Q, did I use, oh, K, sorry. We're going to change the notation to K. Assume the QK are independent and that QK has a chi-squared distribution with RK degrees of freedom. Then, what do we know? Well, we know that the sum of the zi's from 1 to m, I should say the zi squared. Remember, these are standard normal because we're assuming without loss of generality that sigma squared is equal to 1. So in that setting, these are just a bunch of squared standard normals, which takes us to having, and they're independent, so their sum is a chi-squared with m degrees of freedom. Okay, good. And the sum of k from 1 to s of the qk is going to be a chi-squared random variable, and the degrees of freedom, remember, these are also independent chi-squared random variables, and the degrees of freedom are rk. So if we sum them all up, we end up just summing the degrees of freedom, and we get the sum k from 1 to s of the rk for the degrees of freedom. And that's actually what we wanted, because from the theorem statement, we have that the sum of the zi squared is going to equal the sum of the qk, just, I should probably write I from 1 to m, and k from 1 to s, just to indicate this. So since these are the same things, they both have chi-squared distributions, of course, because they're the same thing, and they have to have the same degrees of freedom. We'll say, therefore, m, the degrees of freedom for the sum of the z squareds, is going to have to equal the sum of the ranks of these matrices Rk. So that's the quick way to do the one implication of the theorem, which says that, okay, if the QK are independent and have specific degrees of freedoms, then yeah, it turns out that the sum of the ranks, or the sum of those degrees of freedom, have to be M. All right. So that's that was the easy one. The harder one is to go the other way, because the other way, we're just starting at, well, the conclusion of the first way, which is assume that M is equal to the sum K from 1 to S of Rk. Okay. So then the question is, how in the world do we proceed from here? Well, what we do is we start with, remember, we have A1 matrices, A1 all the way through AS. So what we'll do is we'll start with the first one and work our way from there. So what we do is consider Q1 to be, well, by definition in the theorem statement, Z transpose A1Z. And now we'll denote Q1 prime. I think that was the notation I was using. Is that the notation I was using? And what we'll do is we'll denote A minus 1 to be the sum of all the matrices A except excluding 1. So K from 2 to S, of AK. This is or, because the AKs have to sum up to 1, sum up to the identity, or we have that A minus 1 is just going to be the identity matrix, the M by M identity matrix minus A1. So now this is looking a lot like what we saw in the above lemmas. So these matrices, but I'll just say it, the matrices A1 and A minus 1 are simultaneously diagonalizable, which is the fancy way to say they have the same eigenvectors simultaneously diagonalizable. All right, so what does that mean? Well, that means that effectively that A1 is going to equal something that's going to look like U transpose D, I guess we'll say D1 U, and A minus 1 is going to look like U, I guess we'll say D minus 1, U transpose, D minus 1 U. But the point is the matrix U is the same. And since A1 plus A minus 1 is equal to the identity matrix, we have that D1 plus D minus 1 is also equal to the identity matrix, since the U's are orthonormal. And the rank, well, the rank of A is the rank of D, which means that the rank of D1 is just going to be RK, and the rank of, well, D minus 1 is going to be M minus RK. All right. Therefore, there's only one way this can happen. One way up to ordering, because I guess you could permute the rows or the columns, that this can happen. This can happen, which is to have diagonal entries all ones and zeros. More specifically, what we end up with, again, up to reordering the columns, which we can always apply row and column permutations to reorder them. We have that D1 is going to be in block matrix form, an identity matrix, an R by R1, I guess, an R1 by R1, or an R1 dimensional identity matrix with zeros, zeros, and zeros everywhere else. And D minus 1 is going to be zeros, 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 and an I M minus R1. So it's basically like we took the entire diagonal of ones and we put R of them into D1 and the remaining M minus R into D minus 1. And then what do we get? We'll say, therefore, by lemma 2, we get that Q1, which I guess is just, well, we don't really need to define it. Q1 is just Q1, and Q minus 1, which we'll define as the sum of K from 2 to S of the QK are independent chi-squared with degrees of freedom being R1 and M minus R1 respectively. Okay, so basically we did this for the first. We did Cochran's theorem, but for a single matrix A1. So now we're going to do it all again, but look at the remaining ones. So now consider Q minus 1 and the Q2 through Q S, I guess. And we do the same thing again to get a D2. So we would take Q2 and A2, and we would do the exact same trick of trying to diagonalize it. And what we end up with is something that's going to look like, again, zeros, like this, with an identity matrix that has rank 2 to it, R2 for the dimension. And then we're going to get something that looks like D minus 2, which is going to be the sum of, I guess, D3 through DS for whatever S is, which is going to be 0, 0, 0, 0, 0, 0, 0, 0, I M minus R1 minus R2 for the dimension. Therefore, we get that Q1 from above is going to have be chi-squared with R1 degrees of freedom, and Q2 is going to be chi-squared with R2 degrees of freedom, and Q minus 2 is going to be chi-squared with M minus R1 minus R2 degrees of freedom. So the idea is repeat this for Q3 through QS to conclude. I should point out that these things are all independent. Right? And that's effectively the end of the proof. QED. So again, what we're really doing is when we're doing this proof, we're doing the lemma, but we're doing it, I guess, s-1 times. So we start with the first matrix, which is going to take away r sub 1 ones from the diagonals. We take those out and then we leave whatever's left. And then we go to the next r sub 2 ones and we take those out and we leave whatever's next. And we do this again and again until we've peeled off all of the ones from the diagonal. And what we end up with is a whole bunch of independent chi-squared random variables. Okay, so yeah, that's more or less all I wanted to talk about in this lecture, but I will do a little bit of follow-up exposition because I'm going to save, we're about to start multiple factor or multi-way ANOVA after this, and it's better just to start that on a fresh lecture with a fresh voice and a fresh cup of tea as well. But anyway, let's just say some notes. So the idea is that I'll say in what follows, we will be computing degrees of freedom for complex experimental designs. But it all comes back to Cochran's theorem. Back to Cochran's theorem. I'll say for one-way ANOVA, what we have is we have that, what did we say in the previous lecture? We said that the total sum of squares is going to equal the treatment sum of squares plus the error sum of squares. This is that sum of squares decomposition. Well, we can write this out effectively as just, I guess the vector, is it y? I guess y would be the, no, I guess, well, I'll use z to keep with the notation of this lecture. This is just going to be z times some, well, okay, the total sum of squares does not technically divided by this, the identity, it's the identity minus a matrix of all ones, because we lose 1 degree of freedom for estimating the global mean. So I guess in some sense, what we actually have is we have something that's going to look like z transpose z, and then we're going to have z transpose times the matrix of all ones. This guy is going to be kind of the global mean. I guess we have to divide that whole thing by the sample size, but no, actually, no, we don't. Yeah. Yeah, I'll think about that to make it more precise. I'm kind of just running off the top of the cuff here. But anyway, yeah, so we have this term for the global mean. We would also have our treatment sum of squares, which would be some other z transpose times, we'll say, a treatment. And then we'd have some error sum of squares, which would be something like a times the error sum of squares for z. So really what we're doing is we are decomposing all the degrees of freedom here for the total sum of squares into pieces. So what we would end up with is if we have, say, m degrees of freedom associated with just this quadratic form, then we would end up with, let's say, DOF. Then we would have a single degree of freedom for this piece. We would have our k minus 1 for this piece, and we would have our big N minus k for the last piece. And these degrees of freedom would be the rank of the corresponding matrix. So while in practice you really don't want to have to write out that symmetric matrix, it's kind of a pain and it's quite messy, you can, in some sense, rely on that intuition. And there's lots of different ways to think about degrees of freedom. They're super important when we talk about, well, statistics in general, but specifically for design of experiments. The degrees of freedom can also be thought of as linear subspaces where our data, so our data is m-dimensional in this example, or big N dimensional, I guess. I should actually, I'm mixing my notations here. I should point out that this was maybe supposed to be a capital N, so that it all adds up correctly. But the idea is that our data lives in n dimensions, and each of these quadratic forms lives in some sort of linear subspace that's orthogonal to the other linear subspaces. So if you really like linear algebra, I can draw lots of pictures of that and we can talk about that. If you don't like linear algebra, you can just think of it as counting the amount of data and counting the number of estimated terms and looking at the difference. Either way, it's different ways of intuiting and understanding what degrees of freedom actually are. But yeah, that takes us to more or less everything I wanted to talk about. So I think we'll just stop at this point for lecture number 3. And in the next lecture, we'll get to do a lot of fun because we're going to jump into multiple factor experiments. So we'll have not just one-way ANOVA, but we'll have two-way ANOVA. We'll have blocking. We'll have lots of other crazy things with Latin squares and split plots and things that aren't coming to me at the moment, but I'll look forward to talking to you more about those in the next lecture. So have a good one and see you then.